Okay. So we are also. We were also. Okay.
Let me try again.
Yeah. Thank you.
Okay. This is about a few minutes late, so I hope I have 15 minutes. Um, okay, so my name is Jacob Cebulski of Quantit Australia. This is a small startup. We are focusing on research and on some consulting activities in quantum computing and quantum machine learning in particular. Let me just put my camera off. Okay. So in this talk, I'm going to look at quantum machine learning with Qiskit in particular. I was asked not to show any code, not to step you through the code. So I'm going to talk about concepts and how to develop quantum models and how to avoid problems in those quantum models. Okay. Since we already discussed, we had some sessions which introduce you to quantum machine learning. So I'm not going to talk much about what it is and what are the applications, because we've seen quite a lot of them. But I'm going to look at straight away into modeling aspect, which will be supported with Qiskit. So why Qiskit? Myself, I spent probably equal amount of time with Qiskit and Pendulane. And I can't say which one is better, which one is worse. I like the elegance of Pendulane. I like power of Qiskit. Qiskit supports different programming languages. Of course, the main is Python. Its core is written in Rust, so it's very fast. It also has support for other languages such as C++. It has standard set of quantum state operations. It executes on simulators, quantum hardware, and accelerators such as GPUs. It has fantastic tools for error mitigation and error suppression. It supports a variety of gradient models, which are very, very important for machine learning tasks. And it has a large community of users and community of open source developers. So there's a lot of libraries for chemistry, for machine learning, and for many other fields. Importantly, it supports PyTorch and TensorFlow. So if you cannot find any machine learning model within Qiskit itself, you could borrow them from either of those two environments. It is hardware agnostic, which means that you find many different vendors turning to Qiskit, and you could access the backends via Qiskit. And of course, IBM Quantum backends and runtime are also available. It is considered to be one of the better performers when it comes to quantum platform, but at the same time, it's very complex. So for example, comparing Pendulane to Qiskit, even though I probably use more extensively Qiskit in its production type of environment, and I use Pendulane for research on simulators. So comparing those two, Qiskit is definitely much more complex, and it's probably harder to learn than Pendulane. And also because it's focusing on IBM quantum machines, which are developed very, very rapidly. And IBM wants to turn to the production level software. Its core design changes very, very often. And so it's quite difficult for open source developers to chase and be at the same level as Qiskit core is developing. So you need to be prepared for rapid changes. And if you develop code in Qiskit, the code will have to be adjusted every few months. So when it comes to Qiskit machine learning, it's a very sophisticated environment, which gives you the quantum machine learning tools and techniques and methods. It supports a variety of different models like neural networks, kernel methods, support vector machines, Bayesian modeling, the kernel principal component analysis, and there's a variety of other additional tools which you could borrow from GitHubs and from publications. For example, the clustering algorithms, optimization algorithms, which are built into Qiskit as well. So there's a lot of choice and a very rich environment. Okay, so how do we start with modeling? We rely on parameterized quantum circuits. The normal circuit, the gates would have specific parameters, and those parameters would be fixed. So to make use of machine learning and to be able to train those circuits, the models, you need to be able to create templates of the circuits with placeholders for parameter values. And that's exactly what we do. So we create those templates, and Qiskit supports us with ready-made templates, and you could build custom circuits with your specific parameters, the way you like them to be arranged and used. So this is a typical structure of a Qiskit model. It would have a feature map encoding your data input, the processing, which would feature rotational gates changing and altering the state of the circuit, and entanglements, which would correlate the circuits. This part is the trainable component, and eventually you have state measurement, which could produce results, and those results would normally be passed to a classical optimizer, which would use the classical cost function to determine whether the produced results are far away from anticipated results as determined by the training data set. And so through the iterations, you would eventually, hopefully, would converge the parameter sets to the ideal situations that the circuit produces, for that data set, produces expected results. So that's what normally happens. This is the standard type of structure, but it is not the only structure which you could create for your models. Okay, let's start moving slowly from data encoding to processing and measurements. There's, as Nhalia mentioned, there is a variety of different data encoding strategies, such as basis encoding, angle encoding, amplitude encoding, QRAM encoding, and much, much more. In this particular session, I will focus primarily on angle encoding, and basically for two reasons. One is that at the end of this slides, I have a link to my GitHub, and on this GitHub you could find some exercises which I designed specifically for this session, and those exercises are perhaps advanced. They look at time series analysis using sliding window and creating predictive models which could determine the next step in a time series. So we need to deal with floating point numbers, and because of that, we need to be able to encode floating point numbers which are of any unpredictable values. And so angle encoding is very flexible for that purpose. It's a very simple encoding strategy, and that's what we're going to use in here. The way angle encoding works is that we use rotational operators which change and rotate the state of the qubit around, if you imagine the block sphere, around the x, y, or z coordinate. And on the right-hand side, you can see the a block sphere where the y coordinate is pointing towards us. So it's a simplified version of it. And so what we can do is to change the state of a particular qubit, perhaps turning the state vector to the right and encoding the number associated with that angle, or turning it to the left and encoding negative numbers. And so we would expect that the full scale of the full range of values would be from -pi to pi, or perhaps from 0 to 2 pi. But when you actually want to take advantage of the entire spectrum of values, that may get you into trouble later on. I'll talk about it in a minute. The rotations are always starting from some specific state of the qubit. The most commonly, it's the cat 0 aligned with the z-axis, but you could pick another one. For example, you could use the cat state, which is prepared by Hadamard gate, and then you could use rotations up and down to determine the encoding strategy. And for that, you will have to prepare the state of the qubit appropriately to use and to take advantage of that particular encoding strategy. You could also decide to encode not the angle, but the amplitude, which results from the measurement of that state. So there is a lot of choices you could turn to, relying on very simple state rotation of the qubit. Here is an example of preparing the state of the qubit, encoding 3 rotations, 3 particular values. And when we measure them, depending on how we measure them, you'll have some result. So in this particular case, if we measure it using expectation values, then you'll have 2 positive values and 1 negative value. You'll have to decode it to determine what was the value encoded and what is the result of the measurement. So this is not simply one-to-one relationship between encoding and measurement. You have to do a bit of interpretation of measurement to determine what it was encoded in the first place. There's also a specific technique, which you'll show in a minute. This is repeated encoding of the same value in a circuit, and this is called data re-uploading, and it is known to improve the performance of the model and the performance of the training of the model. So what's the good, the bad, and the ugly of the simplest encoding technique, the angle encoding? There's always problems with every encoding strategy. For example, the amplitude encoding that you may be familiar with, apart from the fact that it's very difficult, it has the side effect that for every value encoded in a circuit, you may generate different structure of the circuit. And that would be difficult to deal with for quantum machines and accelerators, which would have, they would be much more efficient if the structure of the circuit is fixed. So in this case, angle encoding is better because the structure of the circuit is fixed for different values encoded in the circuit. But there's always a problem. So what is the problem here? Imagine that we encode a positive value from 0 to pi in that range. It's quite easy. We can see a value is encoded. If we measure that value, it's a projective measurement on the z-axis. You'll get some negative expectation value if you measure it repeatedly. What happens if we measure it to the left, if we try to encode a negative value? You can see the question marks here. Is it good or bad? Is it a problem? Potentially, this could be a problem because if we measure that particular encoded value, the negative value, and projective measurement on z-axis will give you exactly the same result as the measurement of another value encoded as a positive value. So we have potential measurement conflict instantly after encoding happened. That may not be a problem if you create a quantum neural network and then through multiple rotations in training, that particular, if the rotation happens around the y-axis, it will change the position and optimizer will deal with that somehow. What happens if we try to measure or encode the value which goes beyond minus pi. In this case, you have instant encoding conflict with another value, positive value, and no matter what you do later on, nothing can be fixed. And that will give you problems in optimization and training of the circuit. So here's just two circuits. One is trying to fit the sine function as given by data, and then trying to fit the slightly altered sine function, which stretches it and shifts it, in which case you will never ever be able to train it if you have bad encoding to start with. This is also bad encoding because the range of values that you try to encode for this particular application is from minus 2 pi to plus 2 pi. And so the encoding values wrap around the block sphere and create conflicts. It just happens that in a sine function or cosine function, because of the data has symmetry, the values which are overlapping, which are in conflict, happen to map into the same value on the sine function. But if we stretch it and shift it, those values will be mapping into lower value and higher values and creating conflicts which can all be overcome in any way later on. So beware, you need to pick the right encoding technique. For example, in this case, we may want to pick the range from 0 to pi for all possible values and rescale the values that you try to encode in your circuit. Okay, let's move to the middle part of the circuit, the ansatz, which is parameterized and trainable, full of trainable parameters. And what you instantly can see, it's a very different structure. It's a bizarre structure because we don't have a single block encoding values at the front. So this is the re-uploading case where perhaps the same value is reappearing across different qubits, and then it's reappearing every block. Those are parameterized trainable blocks, and they reappear again, and they're encoded again. So this is very different concept of how to deal with input data in quantum circuits and in classical machine learning. Why would we do this? Well, first of all, we could do this because there may be the need that we want to have more parameters, and the circuit which is creating a function, it takes only one value on input. So if it's one value on input, but you have more than one qubit, what do? Do you encode it only on qubit 0, but not qubit 1? Or should we encode the same value on qubit 0 and qubit 1? Well, it's the choice you have to make. And why encoding it early or later? Maybe we need to prepare the state of the circuit first and then encode the values. That's what's usually done in ZZ feature maps, and this could be done in exactly the same manner with angle encoding. Okay, so what we try to do here by repeating the same value across the circuit in depth, we are basically mimicking the Fourier transform, recursive Fourier transform, which means that the function takes the value, it then alters the value and reapplies this value again, like multiplying the expression by the same value again. We don't multiply it directly, but that's what actually the circuit is attempting to do. It's trying to remind the process what is the value trying to encode. So that's a re-uploading structure where we have parameterized trainable components or layers. And in this case, they are interwoven with encoding blocks, and then you have measurement blocks at the end. And of course, measurement blocks or measurements could appear in the middle of the circuit as well. So they're not necessarily at the end. If you need to reset or reinitialize qubits in the middle of the circuit, you could use measurement for that purpose. There's a danger of that because suddenly the circuit is no longer unitary and you need to deal with that problem as well. So here we have a circuit which has trainable parameters, input parameters encoded, and some entanglements. What else can you do with it? Now we could train those parameters using classical optimizer. We have a whole lot of different optimizers available in Qiskit, and if you don't have enough of them, you could turn to PyTorch, for example. So we have Adam, SPSA optimizer, linear approximation methods like Cobala, very effective within Qiskit, very quickly converging. Nonlinear approximation methods, BFGS, which are harder to use. And then you have optimizers which understand the fact that you're dealing with quantum models and not classical models, like quantum natural gradient optimizers. A lot of different cost functions which those optimizers could rely on, depending on whether you do classification or estimation. So we have R squared, mean absolute error, mean square error, and then cross entropy for classification. And if you want to return the whole probability distribution, you could use Kullback-Leibniz divergence cost function, which compares to distributions. And you could actually train the model based on that. And of course, the circuit could execute on a simulator, on accelerators, and real quantum machines. So we have a lot of choices. You could also build the custom circuit. That's actually a result of custom circuit definition, but you could vary the width, which is number of qubits, the number of layers, the depth of the circuit, the number of parameters. You could actually add more parameters for training without changing the width of your encoding blocks or measurement blocks. You could have like neural network-like structures where the circuit would funnel out first and then funnel in towards the measurements. And you could change the way you entangle your qubits in different structures. So lots of choices, a lot of hard work, but you have this flexibility. Now, at this point, I need to warn you that adding qubits adds parameters and entanglements. So if you add one more qubit, most likely you will have to add some parameters, some entanglements, possibly some extra input encodings. So the number of parameters grows with the number of qubits, but also the number of entanglements grow with the number of qubits. And the states represented by the circuit grow exponentially with the number of qubits. So the complexity grows in every single aspect of the circuit design and then its execution. So now we get to the end, the measurement. How do we organize our measurements? Okay, so we have, again, lots of choices. We could measure all qubits, and then those qubits could be measured independently. For example, measuring single value at a time onto single classical what do you call them? Wires, I should say, registers, classical registers, or you could measure them together to give the probability distribution. Or you could measure a single qubit over a few qubits. So usually we call measurement of all qubits as associated with so-called global cost. And if we measure one or few qubits, it's a local cost measurement. We could also group qubits into groups which are associated with measurements related to different variables. That's especially important when you have very large circuits, and the grouping of measurements may be important to reduce the complexity of the outcomes that the circuit produces. So that's one aspect, how many of those measurements. The second is, what do you do after you got the measurements? Of course, ideally, you should have multiple measurements so that you could actually start understanding distribution of values, which could be interpreted for specific tasks. So for example, if you want to interpret the measurement as a logical value, all you need is measure 1 qubit, do it repeatedly, and then look at the distribution of the outcomes. If there's more zeros in your result, you could interpret it as false, otherwise as truth. But you could also look at the height of that bar and interpret it as a floating point number between 0 and 1. So already we can reinterpret or decode the measurements appropriately for your task. If we measure the probability distribution, so all combinations of qubit measurement outcomes, you build up the distribution, and perhaps you look at the highest, most probable outcome, which could be interpreted as a floating point number. But if you look at the combination of qubit outcomes associated with that most probable outcome, you could interpret it as an integer. So this is the art of understanding or interpreting the measurements for the task you want to train the model to return. Okay, so that's very, very important. Of course, there's if you use Pendulane, for example, Pendulane returns the whole lot of different type of results, expectation values. If you use version 2 of and above of Qiskit, you also have access to different types of measurements and different type of outcomes. For example, variance, you can be returned directly from Qiskit. What's important about measurement, always keep it in mind that measurement destroys the state of the qubit, and measurement loses information. The information associated with the state rotation can be recovered to some extent by doing repetitive measurement, and then you could actually recalculate the angle encoded in the state, eventual state. But what you can't recover is the rotation around the z-axis, which is your phase information. That phase information is completely lost in the measurement. Does it matter? If you use simple classification or estimation, it doesn't matter. But in some applications, like in quantum autoencoders, which are supposed to replicate input on output, the loss of information about the phase could result in the loss of accuracy. So in such a case, you need to have different techniques to measure outcomes, looking at the fidelity, cost function, which are much more complex and probably beyond the scope of this talk. Now, beware that adding a single measurement doubles the number of outcomes. So imagine we add an extra measurement on another qubit, and then suddenly we have as many outcomes with 0, and then the same number of outcomes with 1 of this extra qubit. So number of outcomes doubles. That requires perhaps increasing number of shots to maintain the accuracy of your measurement. So this brings us to measurement nightmares. Again, the good, the bad, and the ugly. Okay, imagine we measure only 2 qubits, and we have 4 possible outcomes looking at the probability distribution. The bars are clearly visible, and we can interpret the results easily. Imagine that we use the same number of shots, but now on 5 qubits. And we have many more outcomes, and some of them are zeros, and some of them are very imprecise. We would imagine that the same circuit would give you similar shape, but we have jagged edge. We lost precision in this process. We lost the precision because we never increased the number of shots to produce the measurement results. So the larger the circuit, the more shots you required when you have a lot of measurements. This is critical because number of shots will determine how long is the computation, how many circuits need to be created and replicated and rerun in a runtime environment. So you need to be careful planning the way you measure your results and how to interpret the results. Also, the more qubits you have, the more entanglements you have, the more quantum errors you're going to generate, and that is going to not only give you imprecision because you don't have enough shots, not enough outcomes and results, but also because there's more errors creeping in. And so you need to deal with them and do some error mitigation or error suppression. And now, since every single vendor is trying to produce larger machines with more qubits, this is not really helpful for many applications. How you deal when you have 1,000 qubits? You can't actually measure 1,000 qubits because then you have 2 to the power of 1,000 outcomes. This is a huge number. Probably we don't have so many, I don't know how many atoms in the universe we have. So we actually need to be very careful and structure our approach to measurement with some design in mind and some wisdom. So number one, instead of working with probability distributions, which scales with 2 to the power of number of qubits, we may need to switch to expectation values, which converge with in a scale of 1 over square of the precision you want to achieve. So suddenly, for large circuits, we no longer talk about shots, we talk about precision, irrespectively how many shots are required. And you can see the precision is independent of number of qubits. When we develop an estimator, as opposed to the sampler, which is used for simpler models, it's possible to group observables into the groups and deal with them separately. Each one is a smaller set of qubits, and we could reduce the number of measurement outcomes in this way. It's also possible to evaluate a very complex Hamiltonian, which is a linear combination of expectation values. And you could group observables into structures of expressions to generate not only less measurements, but also to give you very meaningful outcomes, which could be interpreted readily. That's what's done in quantum chemistry very often. And of course, instead of specifying the number of runtime shots, which is still possible in Qiskit for large circuits, we specify the precision of measurement outcomes. And so that's much simpler, easy to understand. And for expectation values, this is much more computationally efficient. I mentioned the errors in large circuits. And when we work with Qiskit, you are going to engage the runtime model. And that's particularly important for running on IBM quantum machines. The runtime model will automatically inject certain error mitigation strategies at the execution time. So for example, you could specify that you want to have dynamical decoupling or twirling or zero noise extrapolation, probabilistic error cancellation at the execution time. So that's actually very helpful because It means you don't need to worry about special tricks within the logic of the circuit. That could be left for later for the execution time. So Qiskit is very helpful in this regard. Now we're coming to probably the most difficult part, trying to understand the interaction between the Hilbert space, which is where the action takes place, and the parameter space, which is classical space of parameters. This is what's visible to the classical optimizer. So below we have a circuit. That circuit, as it executes, the states evolution is reflected in the Hilbert space, which is actually creating those partial states, correlated states. And basically, we have a path through the Hilbert space of the execution of this particular circuit. The circuit with fixed parameters, which means that if you change your inputs or you change any of the parameters of the circuit, you have a different path through the Hilbert space. That creates a very complex manifold of states representing this circuit. Okay, and so if you look at the optimization in Hilbert space, that's a very complex affair, very complex techniques need to be applied. So some of them are, for example, useful, like looking at the fidelity of the circuit computation, and you could use fidelity cost functions which operate directly on Hilbert space. And there is no simple function you could call to do it. You need to structure the computation and development of the circuit in a particular way to work in a Hilbert space. Now, much simpler operation is to use the classical classical optimizer, which works on the parameter space. But the parameter space, it misses a lot of information about what is the quantum circuit. It doesn't know anything about entanglements. It doesn't know the fact that the parameters are correlated via entanglements because they belong to entangled qubits. It also, we have an issue with gradients. The gradients are attached to each parameter of the circuit, and the gradients are needed to calculate the actual result at the end. The optimizer, the classical optimizer, will see those gradients, but will not understand that those gradients have non-local interactions. If you change one of the parameters in the circuit, through the entanglement, it alters other parameters in the circuit and the gradients as well. So the cost landscape of the parameter space constantly changes. The shape, the geometry of this parameter space is very fluid because we're dealing with a quantum model and not classical model where everything is very static. So the optimizer faces a much harder task to understand relationships between parameters and the gradients, and not always they're going to work. So we need to do a lot of experimentation. We need to do much harder work for us to optimize the circuit. This is basically a replication of information from the previous page. Number one is we have parameter space versus Hilbert space. They're related. They're related via the parameters. The parameter space is classical. The Hilbert space, it's quantum space of states. The data encoding, it brings in classical data into Hilbert space, and the more parameters, the more qubits you have, the more replication in re-uploading, the richer is the representation of data in the Hilbert space. Entanglements, they impose relationships on qubits and relationships on data entered as input, but also relationships between the parameters, the trainable parameters. The circuit becomes more expressive. That means it has better representation, richer representation in Hilbert space. But at the same time, the more parameters you have, the flatter becomes the cost landscape and harder it is to train the model. The more entanglements you have, the more non-local interactions you have between the parameters belonging to different qubits. So the optimizer has harder job to do its task. So this is a very interesting phenomenon. It's very different from typical classical machine learning. Okay, I mentioned that if we have more parameters, more qubits, we have high dimension Hilbert space, and we also have high dimensionality of the parameter space. Is this a problem? It is a huge problem, which is known as the barren plateau. The barren plateau basically indicates that the cost landscape of your model, the errors generated by a model, they become flat, and the optimizer has difficulty finding the values down towards the lowest cost of that particular parameterization of the model. Why is this happening? Some people say the problem is the number of qubits. Some other people say the problem is the number of layers and the depth of the circuit. Other people say the problem is because of the random parameterization of the initial values of the parameters. What's the truth? The truth is pure geometry of high-dimensional spaces. Let me explain what's happening. Imagine that you have a space of parameters which is enclosed in a ball. If the ball is two-dimensional, it's a circuit, and all parameters are dots within that ball. If the ball is three-dimensional, it's a sphere, and all the parameters would be within the sphere. And then you could imagine we have four-dimensional, five-dimensional, and 45-dimensional ball. So we add the dimensions to the ball. It's harder to imagine, but let's imagine we can project it onto 2 dimensions on this slide. The curious thing is that intuition tells us that as the number of dimensions grow, the volume within that ball is going to grow as well. Well, this is actually not true. The highest volume of n-dimensional ball is 5. And so initially it's smaller volume, then the volume grows to 5, and then it reduces with the number of dimensions. Now what happens is that the actual surface of that ball is going to grow, but the volume shrinks. So what happens there? It means the volume concentrates around the surface of that n-dimensional ball. So what happens when you have a low-dimensional ball? Let's say in 4-dimensional space. That means that there's a lot of volume, and if you want to represent the error, the elevation of your landscape, there's plenty of space to put the valleys and hills of the landscape within the ball. The high elevation indicates that it's closer to the surface. The lowest elevation, the lowest error, it means it's closer to the middle of the ball. And so if you pick any point on the surface, the optimizer finds the way down toward the optimum parameterization of the model. No problems. Imagine you have a 45-dimensional ball, the parameter space. Now, since most of the volume concentrates around the surface, it means there's less space available to represent the elevation, the heights and dips, which is the error level represented in a cost landscape. Now, if we are very far from the optimum, then optimizer will find it a really difficult way to find the way down because everything is flat in the surface. It also means that if you use random parameterization, that means you land anywhere within this ball, either close or far away from the optimum. So here we are. We have a barren plateau just because of the geometry of multidimensional spaces. I did some simulation of that fact, and I found that for high-dimensional balls, the distances between within that ball, they concentrate around the mean. So almost every distance is the same in high-dimensional spaces. Now, is there any solutions to the problem? Yes, use fewer qubits, fewer layers, fewer parameters, use local cost functions so that we don't have this sparsity of outcomes. Perhaps use non-Euclidean metrics so that it could have another measurement of error, which could amplify those small distances. We could also be aware of random parameter initialization. So for example, in quantum chemistry, we would run the model on classical machine to find as close parameterization to the optimum, and only then move into quantum machine so we could find more precise result. You could also use barren plateau resistant model design, perhaps design layer by layer. So each layer has only a small number of parameters. And we could use barren plateau resistant models, such as quantum convolutional neural networks, where the filter doing convolutions around your data is small dimensional. So we never get into high dimensional spaces. Okay, so how do we actually go about working within Qiskit to train the model? So first of all, we need to define a circuit, custom or using templates. And this circuit will have to be transpiled, which means it has to be mapped onto the architecture of your quantum machine. It means that the logical qubits, which are close together in the circuit, perhaps they're far apart on a real quantum machine. And so they need to be reshuffled appropriately. It could be your circuit is only 5 qubits, but the quantum machine has 100 qubits, which means that they need to be mapped appropriately and the space needs to be filled up. So there's a lot of work in transpilation, mapping your parameterized quantum circuit onto real hardware. Then you need to specify which of the parameters are weights, the trainable weights, which of the parameters are inputs. You need to identify how to initialize them to start with for the optimization. You need to determine how you're going to measure the outcomes, define observables. And again, those observables need to be aware of the quantum machine. So the actual circuit is transpiled, but observable need to be mapped onto the layout of all the parameters and the qubits in the machine. And you need to specify the type of gradients which you're going to use in this process, whether it's a JAX or NumPy gradients or torch gradients. Different gradients, approaches to gradient manipulation by different software vendors and hardware vendors may need to be in use, especially if you use a gradient-aware optimizer. Okay, so all of this need to be mapped onto your Hilbert space. And this is responsibility of the estimator. The estimator is a piece of software which brings all this information together and maps it onto the vector space of the Hilbert space, the state space. For that, it will need the help of the particular estimated primitive, which will understand whether you're going to do execution later on a real hardware quantum machine or the accelerator like GPU, or if you're going to run it on a CPU. The actual optimization will be done by the classical optimizer, but it needs to be embedded into the actual software layer of which includes this quantum computation. That's done by the regressor. The regressor, it will understand that it needs to initialize the circuit and then will talk to the optimizer, which will do the forward and backwards passes, and will vary the parameters of the circuit appropriately, which could utilize the loss function and which possibly do the callback to keep track of what's happening and what results are being generated at each iteration of the optimization. And this itself needs to be under some process of experimentation. There's a lot of work to be done. So for example, I was developing on my GitHub, I have an example with step-by-step changes to the model. I want to develop a model to fit a slightly more complex data. The two sign functions dependent on each other, the training part and the testing part. When we just start running first go, the model gets terribly undertrained with a very poor fit. You can see there's more work to be done in training, but then we could increase the number of epochs. We could play with the initialization weights, making it smaller and better controlled. And the model perhaps is still undertrained. You can see that the real values and the predicted values are still far apart. There's a lot of more work was done. I played with number of layers. I played with different types of observables, global cost function, local cost function. I used different optimizer, and eventually I got a really good convergence in both training data and test data. As you can see here, excellent fit of data. Now we've got a ready-made model. Would it be applicable to other data, the other time series? No. So if we use the same model for different data, suddenly nothing works. I need to start again from scratch, really playing and changing different parameters of your model. Eventually, you may get results which can still be improved. So is that all? No, that's not all, because quantum models are highly sensitive to initialization. So if you're going to run the best model possible you got and change initialization of that model to 5 different random sets of values, you're going to find out that you may get terrible, huge variance in the results. So in 5 times, the best model is a good fit. The median model is a poor fit. The worst model is terrible fit. So what do we do about that? We need to go back and start playing with the model so that your average model is pretty good. And you never pick the best fit to report to your paying customer, because that would be lying. If the customer changes your test data, suddenly the model gives you this. So you need to be honest about the performance of the model and don't play with the best result. Play with your average result, play with the median model fit, and report it honestly. Okay, there's a lot more to be done. Some reading. I recommend with the book Dancing with Qubits by Robert Suter, the 2nd edition. It gives you a really good introduction to mathematics for quantum computing, not quantum machine learning. The book by Maria Schult and Francesco Petruccioni, Machine Learning with Quantum Computers, 2nd edition. It's a fantastic book which gives you an overview of the theory behind quantum machine learning. If you prefer a more practical introduction, then there's a great book by Elias Combaro and Samuel Gonzalez Castillo, Quantum Machine Learning and Quantum Optimization. It actually uses a variety of different quantum platforms to illustrate concepts. 2 great articles, one to give you the summary of Qiskit, another one which gives you a really good introduction to Qiskit machine learning. And I find that it's a must read, because you should read those articles cover to cover, because the documentation of all quantum platforms are very poor, and they issue those articles and you could find jewels that you can't find anywhere in the documentation. So currently Qiskit SDK is 2.2 or maybe 2.2.3. But at the moment, Qiskit is far ahead of other libraries, open source libraries, including the Qiskit machine learning. So Qiskit machine learning works well with Qiskit SDK 1.44, which means it doesn't have the benefit of Qiskit version 2 primitives, but it's catching up, and hopefully we'll see the new edition of Qiskit machine learning, which uses all of the different new features of Qiskit. So summary of this, QML is intersection of quantum computing, machine learning, and maths, and it's hard. It's hard because we have so many different types of bodies of knowledge that we need to be aware of. If you're a physicist, you may be missing machine learning. If you're a computer scientist, you will definitely be missing quantum mechanics, and mathematics is hard. Qiskit itself provides a great platform for quantum machine learning, and quantum machine learning models in Qiskit are based on parameterized quantum circuits, which are unlike what you find in Pendulane. Pendulane gives you a very elegant view of the circuit, which is a function, but it uses differentiable computing paradigm, which is very different from everybody else's. But it's a very nice, elegant quantum computation. The most common approach to optimizing quantum machine learning are variational quantum algorithms. And you've learned about them from other modules in this workshop. Quantum encoding is vital to the success, but it's full of traps. You need to be aware of those traps depending on what strategy you're going to use. And usually you get aware of them too late. So measurement is important. The circuit design needs to consider the state evolution in Hilbert space and parameter optimization in classical parameter space. They have conflicting requirements: expressivity versus trainability. Dimensionality is hell. You need to deal with that. Keep everything low dimensional if possible. QML is still a research discipline, and you need to do a lot of experimenting. And to show advantage of any model over a classical model, you need to be clever of what happens in Hilbert space. So that's about it. Thank you so much. If you have any questions, you're welcome. By the way, I started late, about 20 minutes, so I'm well inside my time.
Thank you so much. So do we have any questions? Question from the online audience. Please unmute yourself and ask the question.
Yes, I have some question.
Yep.
Yes, I have one question about the data encoding method. So what is the...
Hello?
Can you hear me?
I just lost you somewhere. Okay, try again.
Yes, I would like to ask you about that data encoding.
Yep.
So based on the quantum machine learning method, do you have some advice for using some data encoding method? Because they have some, because depending on the cases, they may have some trade-off between the high accuracy and the how to say, and the depth of the quantum circuit.
Okay. All right. So look, if you use something like quantum neural networks, one of the best feature maps is ZZ feature map, which nicely distributes the initial states of your circuit in the quantum space. Okay, so and it has a lot of, in Qiskit you have a lot of parameterization. You could have repeated blocks and so on. So that's a very good starting point. If you create your custom circuit, I usually go for the simplest things like angle encoding, and that's because I'm running a lot of optimization on GPUs, and I want to be ready for quantum computation. If you want to optimize it on GPU, you want the circuit not to change with every data you encode it. If you use amplitude encoding, this is the effect you're going to get. Amplitude encoding is fantastic because your encoding is identical to measurement, but it has some side effects, and you will not be able to run it on accelerators, for example. So you need to really think about encoding depending on the problem you have, and the problem will really guide you to which encoding strategy is best. One thing is there was a study done looking at different models people developed, and they found that one thing in common between all these models, the models which had re-uploading of data, they were the best performing models overall. So you need to think about re-uploading the data, repeating encoding blocks throughout the circuit, and that gives you, it's a more complex for advanced quantum machine learning developers, but it's a very effective way of improving your model performance.
Thank you. So, is there any question from online and on-site?
There's some messages there which I may have missed. Does Qiskit provide the quantum natural gradient optimization function? Yeah, I think so. I haven't used it. I know that Pendelane has a quantum natural gradients. Definitely, there is a. I think there is a quantum natural gradient optimization. I'll have to check, but I don't know whether it belongs to quantum machine learning or it belongs to the core.
Thank you.
It's
Yes.
Yep.
Thank you, Jacob. I think it's
Thank you so much.
I think it's very late in Australia. I'm sorry about this.
It's okay.
Yes. Hopefully you have good time with us in Paris-Saclay. Next time,
Okay.
hopefully we can host you in person.
No worries. Thank you so much, and goodbye. If you have any questions, I'm available on LinkedIn. Send me questions there.
Yeah, we will
Okay.
contact you via Discord. Don't worry, you are Discord channel.
Thank you.
Thank you. Okay, so I think I suggest we'll have a 15-minute coffee break before moving on to the hand-on exercise. Hello everyone, welcome back after the coffee break. So please, I would like to introduce Jim from Qiskit. Jim, please come back to give us about hand-on exercise about quantum machine learning. Please turn on your voice.
Yes, hello, Ben.
Yes, everything is perfect. Please share
Okay.
the.
I'll share my screen.
Yeah, we can see you now. See the screen now.
All right. Hello, everyone again. So good afternoon in Paris. And I suppose that most of the concepts have been covered in the previous session. So I think you can just take my presentation as a kind of brief review focusing on the practical stuff. And so today I'll be working through the practice notebook on data encoding in quantum machine learning. And this is the first session, and we have another second session for applying this, for the quantum kernel and VQC and QNN. So in this session, we'll explore how classical data transforms into quantum states. Okay. So for those of you meeting me for the first time, I'm a PhD candidate at Qiskit again, and I focus on the experimental quantum simulation and some hardware techniques like optical tweezers. And at the same time, I'm working on theoretical aspects with Bin's team. So let's begin. The central question we are addressing today is like, how do we actually transform classical data into quantum states, right? The transformation is what we call the feature mapping in machine learning. And we are mapping our classical features into quantum Hilbert space. And what makes this interesting is that Hilbert space grows exponentially with the number of qubits. So the notebook will work through give us 6 fundamental encoding methods and plus 4 production-ready feature maps from Qiskit that people actually use in research. So each section follows the same helpful pattern where there's a conceptual explanation first, and then you have working code you can run, and then we have exercises where you get the hands-on practice. Okay, so let's see how this classical to quantum transformation actually works. And this will be the roadmap for our today. So we'll cover 5 basic encoding methods on the left side, starting from basis encoding and amplitude encoding, angle encoding, and there's phase encoding and DAE on the last. And then we'll move to the more sophisticated built-in feature maps on the right. Here we have efficient SU2, Z feature map, ZZ feature map, and lastly Pauli feature map. So the thing is that each of these approaches has different strengths and trade-offs, and understanding when to use which one is would be the art of the quantum machine learning, right? Okay. So now let's start with the basis encoding, which is the most straightforward approach. So the idea is very simple. Basically, just convert your numbers to binary representation, and each bit becomes a computational basis based on qubit. So looking at the example here, the number 5 in 4-bit binary is, of course, 0101. and each bit maps directly to either the 0 state or the 1 state shown on the right side of the slide. So if you're encoding, for instance, 3 numbers like 570, you will get this 12 qubit state, and the 4 numbers are corresponding to each numbers, right? And the structure is perfectly preserved, and nothing gets lost in the translation. Now the limitation here is that using 1 qubit per classical bit, and you're not leveraging quantum properties like superposition or entanglement. So this makes it classically simulatable. A classical computer can easily track when basis state you're in. But even though it's simple, we're still doing feature mapping by transforming our data into a different representation space. And that's the key insight for this slide. And now we have amplitude encoding, which takes a completely different philosophical approach. So instead of mapping bits to basis states, your actual data values becomes the probability amplitudes of the quantum state itself. So we have, take the example here, vector 485. You normalize it, and those values become the coefficients you see here, 4 over root 105 times the 0 state plus 8 over root 105 times the 1 state, and so on. Here's what the Hilbert space dimensionality really matters. With n qubits, you can encode 2 to the power of n amplitude values. And so looking at the chart on the right, 2 qubits gives you 4 value, and 3 qubit gives you 8 values, and 10 qubit gives you 1024 values, and that's the exponential scaling. But there's a trade-off. So preparing these specific amplitude patterns requires deep, complex circuits. And on noisy hardware, circuit depth is your enemy because errors accumulate with every gate operation. So amplitude encoding is hard to prepare, but it's also hard for a classical computer to simulate. And this is where potential quantum advantage could emerge. Now, let's talk about the rotation-based encodings. Looking at the blow sphere on the right, we have different types of rotation gates ongoing. It's a diagram for representing rotation gates. And anchor encoding is probably the most popular method in current applications. Each feature becomes a rotation around the y-axis. So you apply an RY gate where the angle theta is your feature value. This fundamentally differs from amplitude encoding. Rotation-based methods use the geometric structure of individual qubits, while the amplitude encoding prepares the patterns across the entire multi-qubit state space. Phase encoding here is quite more subtle. You're encoding information in the relative phase between the 0 and the 1 state. You start with the Hadamard gate to create superposition, then apply a phase rotation. The amplitudes stay equal, but there's a hidden phase information that reveals itself later through the interference effects. Then lastly, dense angle encoding is the efficient option. It uses both RY and RZ rotations on a single qubit to encode 2 features instead of 1. So basically this means that if you have 12 features, you need only 6 qubits instead of 12, so which is crucial when qubits are limited. Now we move to the sophisticated built-in feature maps that combine encoding with entanglements. Looking at the circuit diagram on the right, efficient SU2 uses layers of 3 rotations, RY, RZ, RY, followed by entangling CNOT gates. The reps parameter controls how many times you repeat this same layer structure. Z feature map alternates Hadamard gates and phase rotations, but keeps everything separable, so there's no entanglement. This makes it classically simulatable, but also but also it's the noise resistance since it avoids those error-prone 2 qubits. ZZ feature map is where we introduce entanglement through our ZZ gates here that couple pair of qubits. Well, this is not the real representation of our ZZ gates. It's just simplified representation I've used, but you will see the real one through your hands-on notebooks that we provided. Okay. And now we can capture feature correlation relationships between features, not just individual ones. The entanglement pattern matters because, like linear connects adjacent adjacent qubits, and the circular wraps them into a ring, and the fall connects like everything to everything. Now this slide shows the fundamental difference that entanglement makes in how data is represented. On the top here, without entanglement, each qubit is independent. The quantum state is a product state, so you can write it as a tensor product of psi1, psi2, and psi3. Each feature is encoded separately and isolated. On the bottom, with entanglement qubits become correlated. The state is no longer a simple product. So features can influence each other, which lets you represent like joint relationships. This is crucial for problems like image processing that we will see in the next session, where like neighboring pixels are related, or time series analysis, where the consecutive data points depend on each other. More entangling connections mean richer interactions between features. But there's a cost, more 2 qubit gates, which brings us to the hardware constraints. The Pauli feature map is the most general and flexible framework we have. So you can specify any combination of Pauli operators, X, Y, Z, for single qubits or multi-qubit terms like XX, YZ, and ZZ. But so why do we call this a general framework? That's because all the other feature maps we've discussed are like essentially the special cases. If you choose the right Pauli strings, so you can recreate the Z feature map and the ZZ feature map, or pretty much like any other encoding strategy. So it's like having a unified language that can express all the different dialects. So this makes it incredibly powerful for experimenting with different encoding approaches. Now let's talk about what actually determines success on real quantum hardware. The critical factor is, as I mentioned, the CNOT gate counts. So looking at the comparison chart here, you can see how different feature maps accumulate to cubic gates as you scale up the features. But why does this matter so much? Well, that's because the two cubic gates like CNOT are the main source of noise and errors. Their error rates are typically 10 to 100 times higher than a single qubit. In the comparison, Z feature map has 0 CX gates, so it's completely noise resistant. And ZZ and Pauli maps accumulate CNOT gates with more features and entanglements. And the efficient SU2 sits somewhere in the middle. So what we are doing here is we are looking for a sweet spot, complex enough to be hard for classical computers to simulate, but simple enough to run reliably on noisy hardware. So basically, it's a balance between complexity and implementability. Now, this brings us to a fundamental question. What makes a feature map quantum advantageous versus classical simulators? I mean, the classically simulatable. The requirements are clear. You need entanglement and interference things that are hard for classical computers to simulate efficiently. But it also has to be implementable on noisy hardware without falling apart. The challenge is that more repetitions mean more expressivity in theory. You're exploring richer feature space with more parameters. But every gate operation introduces some probability of error. So eventually the noise accumulates and overwhelms whatever benefit you're getting from the increased expressivity. So the optimal strategy is to find that balance between expressivity and noise. Sometimes a simpler encoding with less entanglement actually performs better because it's more robust to the noise environment. On real hardware, robust encodings often win over theoretically more powerful but fragile ones. So to wrap things up, I've included a quick self section at the end of the notebook. And these are the multiple choice question you'll see there. And you can just first work on the workflow of each notebooks. And if you have more time left, you can go through these wrap-up questions. And so here are the key takeaways from today's session. The art of quantum machine learning is really about like balancing theoretical power against practical constraints. You need to monitor circuit depth and CX gate counts. These aren't just like abstract numbers, they're like the real constraints that determine whether your algorithm will work on actual hardwares. And the design framework we built today shows that encoding equals feature mapping into Hilbert space. Entanglement fundamentally changes how data is represented from the isolated to correlated. And the Pauli feature map unifies all these different approaches into one flexible framework. So as you work through the practice exercises, please try to pay attention to the circuit metrics. So you can see what insights emerge as you're experiment with different encodings. And this is it for the first session. Thank you for your attention, and you can download the day 4 notebook for this session, and I'll come back after about 30 minutes from now with the going through the solutions. Okay, so and please upload any questions if you have in the Discord channel. We have specific channels on the Discord, so please ask through Discord, and I'll be very active. And thank you very much.
So thank you, Jim, for the presentation. So we will give the participants a little bit time to practice, and if they have any question, they will ask us. So hello everybody, welcome to the event. So I think you had very good time for today's sections, and we have very many quality talks today. So right now I would like to close the day four section of our event. Tomorrow we will have a very high quality talks from IBM Quantum, Sandu, and CNRS Singapore. Hopefully, we will have they will have many people to join us, and see you tomorrow.
All right. Bin, can you hear me? Uh, Bin?
Yes,
Oh, do you hear me?
yes.
Okay.
Yes, so we can see your screen now. Please start.
Okay, so I'll quickly go through the next session parts for the quantum kernels and VQC and QNN. We'll work through the so this is the practice notebook walkthrough for the actual quantum machine learning. Okay, so first I will start with the central question that we're addressing today. Like, how do we actually use quantum feature maps for like machine learning? You've already seen how the feature encoding works from the first session, and now we need to understand how to leverage those encoded quantum states for classification tasks. And there are two main paths to solutions here. It is important to understand that these are distinct strategies you can choose from. Like, it's not the steps in a single process. The first path is the quantum kernels, which use fixed maps combined with classical machine learning. The second path is the variational quantum classifiers, or VQCs, which are trainable quantum circuits that learn on their own. Well, both approaches gives us the different ways to harness like quantum computing for solving real problems. Let me give you an overview of these two approaches and how they differ. So starting with quantum kernels, the key idea is to estimate kernel matrices via quantum state overlaps. We measure how similar quantum states are, and that becomes our kernel value. Then we feed those kernel matrices like into a classical support vector machine with a pre-computed kernel. The feature maps are fixed, but meaning we don't train any quantum parameters. So it's a hybrid approach where quantum assists features and classical handles the learning. Now for the variational quantum classifiers and the quantum neural networks, these use a different architecture built from these three components, which is a feature map, an ansatz, and an observable. We train these circuits with a classical optimizer called Cobilla. The quantum circuits have adjustable parameters that we optimize during training. So this gives us an end-to-end quantum model that makes direct predictions. The key difference is that VQCs are the trainable quantum circuits, whereas kernels use fixed feature maps. All right, now let's dive deeper into the quantum kernels with the big picture workflow. The quantum kernel method follows 4 clear steps. So for the step 1 is mapping inputs to a quantum states. We encode classical data points using a feature map of phi of x. And the step 2 is optimizing circuits for the backend. We apply transpilation with optimization level 3 for efficient execution on the real quantum hardware. And the step 3 here is the executing with quantum primitives. We run circuits using samplers to get measurement results. And lastly, step 4 is the post-processing results. We convert those probability measurements into kernel entries and build kernel matrices. So the ultimate goal here is to build kernel matrices that classical SVM algorithm can use. And this let us leverage quantum feature spaces while still using well-established classical machine learning methods. Now, let me explain how we compute the single kernel value through overlap measurement. So for 2 data points, xi and xj, we encode each one into quantum states. In the implementation, we use Z-feature map to encode classical data. Then we combine them with the unitary overlap to measure similarity. And here's how it works mechanically. We prepare the first state using phi of xi. Then we apply the adjoint of phi of xj, which effectively reversing the second state's preparation. The kernel value k of x, k of xi, comma xj equals to the overlap between these states. The sampler primitive estimates the probability of measuring all zeros. So you can think of it this way, like if the 2 points are identical, the second circuit perfectly undoes the first one and returning us to the zero state. So when we get a high probability of all zeros, that means high similarity in the feature space. And this probability directly becomes our kernel matrix entry. Now let's scale from a single entry to the full kernel matrix for SVM. The practice notebook uses a dataset with 128 rows, and there's 14 features and labels in the set -1, comma, and +1. We need to compute two matrices. There's K-train that captures all pairwise similarities among training samples, and there's K-test, compares the test samples against training samples. So each entry Kij equals the probability we just discussed. And once we have the matrices, we feed them into scikit-learn's SVC with kernel equals pre-computed. And like this is a very beautiful hybrid flow. And so the quantum handles the computing the kernel values, and the classical handles the SVM optimization to like find decision boundaries. So the quantum computer becomes a specialized coprocessor for computing kernel values in exponentially large spaces that classical computers cannot efficiently assess. Now we need to face the NISQ reality about circuit depth. Even though we are using a simulator today for speed, we must design our circuits as if they were running on real hardware. So the 2 cubic gate depth is the primary bottleneck on NISQ hardware. And CNIT gates have error rates that are 10 to 100 times higher than single cubic gates. So let me break down what different depth ranges mean. If your qubit depth is less than or equal to 10, you're generally robust with good fidelity. And between 10 and 50, performance becomes variable and you may need error mitigation. And above 50, things get very noisy. So the thing is that the qubit depth greater than 100 is generally a non-starter on today's hardware. So what can we do about this? We have several optimization strategies here. First, design custom entangler maps aligned with your data structure. Second, repeat transpilation multiple times and select the minimal depth circuit. And last, there's a transpile with optimization level 3 for minimal gate count. And the goal is so to get the circuits shallow enough to run reliably while expressive enough to solve the problem. And for the quantum kernels, it includes 10 self-check questions. There won't be any code practice for this notebook. So you can take your time going through the concepts and trying to understand the workflow. Now we shift to the we shift from fixed quantum kernels to the trainable parameterized quantum circuits. The goal here is to building end-to-end quantum models trained by classical optimizers. The task we'll use is classifying horizontal versus the vertical line images with just 8 pixels. So we're moving from measuring similarities to building trainable circuits that learn directly from data. A variational quantum classifier builds a function that maps classical inputs to quantum predictions. The function is the f theta of x equals the expectation value we compute from our quantum circuit. So let me break down the three components. The feature map u of x encodes classical data into quantum states, just like we saw with the kernels. The trainable ansatz w of theta is a circuit with parameters that get optimized during training. And the observable O is a measurement operator whose expectation value becomes our prediction. It's important to understand that this is a quantum parametric modeling rather than the strict neural network layers. The term quantum neural network is something used, but the analogy to classical neural networks isn't exact. Parameterized quantum circuits don't need to follow layered structures. So the key point is that we're training quantum circuits to learn the classification boundaries. The VQC practice notebook uses a simple but illustrative problem. We're working with 8 pixel images arranged in a 2x4 grid, and each image shows either a horizontal line or a vertical line. And this is a binary classification task. Horizontal lines get the label for -1, shown as a bright line in the first row, and the vertical lines get label +1, shown as a bright line in the first column. To make it realistic, non-line pixels contain random noise values. We split the dataset with 70% for training and 30% for testing. For encoding, we use an angular Z feature map with 1 qubit per pixel. The dataset is intentionally simple, so we can quite focus on understanding the quantum methodology rather than the classical difficulty. Now, when we first build a model with the basic ansatz design, we get around 60% accuracy on both training and testing. So here's the initial ansatz that we use. It uses 2 rotation layers, Ry and Rx, with limited CNATs. The CNAT pattern only connects qubits 0 to 1, 1 to 2, and 2 to 3, covering just the top row. The circuit depth is 5 with 2 qubit depths of 3. So what's the diagnosis of why performance is limited? And it is not because we didn't train enough. It's a fundamental design flaw. The entanglement pattern misses the key pixel adjacencies. Specifically, bottom row pixels, which are 4 through 7, have no entanglement at all. The circuit simply cannot compare the top row with the bottom row. So because of this disconnected design, the circuit cannot learn horizontal patterns across the whole image. And we need to align the entanglement pattern with the data structure to get better performance. And now let me break down the architecture components in detail. First, the feature map U of X encodes 8 pixel values into quantum states using angle or Z rotations. This part is non-trainable, just like in quantum kernels. Second, the ansatz W of theta uses the parameterized Ry and Rx rotation layers with the strategic CNOT entanglement pattern. This is trainable part where theta represents our parameters. And third, the observable O uses the tensor products of Z operators. The expectation value lies between -1 and +1, which matches our label range perfectly. Now for the loss function, we use a mean squared error between predictions and true levels. And for the optimizer, we use Cobilla. Cobilla is a derivative-free and noise-tolerant, which makes it well suited for NISQ hardware where gradients are hard to compute. Now, for the primitive, we use estimator, which computes the observable expectation values. The shots parameter controls the statistical precision, and all these components work together in the formula f theta of x equals the expectation value of our observable. The fix for our 60% accuracy is to extend the CNOTs to capture horizontal adjacency on both rows. We add connections for qubit 4 to 5, 5 to 6, and 6 to 7, alongside the existing top row connections. So the full pattern covers both rows. But notice that the circuit depth remains unchanged. We are not adding more layers, just better utilizing the entanglement within the same layer. The capacity is now aligned with the problem structure. The expected improvements are better convergence during training, higher classification accuracy, and importantly, the same circuit depth, so no additional computational cost. The entanglement pattern now captures the structure of horizontal adjacency in both rows. And this demonstrates a key principle in quantum circuit design, which is sometimes the solution isn't more parameters or deeper circuits, but the better architectural choices. So the notebook for VQC practice, we have 8 self-check questions. And yeah, you can just basically go through the workflow and check your concepts understanding. And now let me summarize the key takeaways with 2 philosophies and 3 practical lessons. So first, quantum kernels use fixed quantum feature maps to access exponentially large Hilbert spaces. And the classical SVM handles the optimization, giving us the quantum-assisted features with classical learning. Second, VQCs and QNNs are trainable quantum circuits end-to-end. They use feature map plus ANSYS plus and observable architecture. Parameters get optimized with classical methods, but the model itself is encoded directly in the quantum hardware. Now for the practical lessons, the first lesson is align entanglements with data. Circuit structure should reflect problem structure, and custom entanglement patterns yield better performance with the same depth. The second lesson is the control 2-qubit depth. The hardware reality is that depth greater than 100 is a non-starter. So transpile aggressively, repeat for best results, and minimize the CNOT gates. And the last lesson is to use primitives appropriately. Sampler for probabilities when computing kernels, estimator for expectation values when training VQCs, and choose simulator versus hardware based on your scale and noise tolerance. So this is it for all the sessions, and Thank you very much. I hope you enjoy exploring the quantum machine learning techniques through the notebooks. Thank you.
Hello guys, I hope that you have a lot of fun for today's section. So right now I would like to close today's section and see you tomorrow.